Good morning. We are Group 3 and we will be presenting the topic Taylor and Power series.
Hi, my name is Maja Zhu, and today I will introduce alternating series. An alternating series is an infinite series whose consecutive terms alternate between the positive and the negative values. The general form is look like this. While the an is positive, the factor -1 powered by n plus 1 changes the sign of each term, creating the alternating pattern. A simple example looks like this. A minus 1 over 2 plus 1 over 3 minus 1 over 4. Yes, and while each term changes from the positive to negative repeatedly. Unlike an ordinary series, an alternating series has the special properties, and under the certain conditions, it can converge to a finite value. Alternating series is closely connected to several concepts that we have learned in calculus. It begins with a sequence which provides the individual terms. When we add those terms together, we obtain a series. For an infinite series, one important question is whether it converges or diverges. An alternating series is a special type of infinite series that often converges under the suitable conditions. My teammate will explain those conditions in the next section. Besides its mathematics importance, alternating series also has many real-life applications. It is widely used in numerical approximation, scientific computing, and computer algorithms. For example, the natural logarithm of 2 can be represented by the alternating series. By adding more terms, computers can produce increasingly accurate approximations. This idea is widely used in scientific software engineering, calculation, and many mathematics applications. So, thank you.
Now let we talk about the example 1. Sum from n equal 1 to infinity of negative 1 raised to the power n plus 1 over m. We use the alternating series test, which has two rules. First, take the positive part. A sub n equal 1 over m. Rule 1 time limited of 1 over n as n approaching infinity is 0. This condition is satisfied. Rule 2 check if the squeeze is decreasing. 1 over n is always bigger than 1 over m plus 1, so the teams keep getting smaller. Both rules are fulfilled, therefore this series is convergent. Example 2. Sum from n equal 1 to infinity of negative 1 to the n times n squared over n squared plus 5. First, we take out the positive part, so a sub n equal n squared over n squared plus 5. For alternating series test, the first rule is checking is limited. The limit of the sub n as n approaches infinity equals 1, which is not 0. Since the first condition false, we do not need to check the second rule. This series does not meet the test requirements, so it is divergence.
And so for my part, I will be presenting about the power series. There are two general forms for the series, as you can see, where x refers to a variable and cn are constants that act as coefficients. The first form is when the series is centered at x equals to 0, meanwhile the second form is when x is equal to a, where a is a constant. And for the convergence section, how do you determine if a power series converges? There are three example of cases. Firstly, is when a series only converges when x is exactly equal to a, meanwhile diverges when x is not equal to a. Therefore, our radius of convergence is 0. By the way, radius of convergence refers to the physical distance from the center of the series to the boundary of that interval. Other than that, a series also converges for all real numbers of x, therefore the radius is infinite. And lastly is the case where radius are bigger than 0. Convergence happens when the distance between x and a is less than r, meanwhile diverges if the distance of x minus a is bigger than r. And lastly is our interval radius section. The interval of convergence is the range of numbers where our power series works, and the radius, as I've mentioned just now. To find these values, we apply the ratio test or the root test to the series, and if the series is centered at 0, our interval is strictly between negative r and positive, and our radius is simply r. If the series is centered at a, the entire interval shifts with a range between negative r plus a and r plus a. Meanwhile, the radius also remains r. Once we have these boundaries, we have to test the exact endpoints. Moving on to the real-life application of power series, there are two examples, which is for field of engineering and second is physics. In engineering, specifically spectrum analysis, is to receive wide range of frequencies and pinpoint which one has the loudest volume or the brightest light. For the physics section, power series is being used for complex problems such as oscillatory or harmonic motion and perturbations, where we find approximate solutions for them. So for the oscillatory motion, a displacement function is expanded to a power series to smaller oscillations. Meanwhile, in the perturbation theory, when an exact solution to a problem is hard to deal with, we use series approximation that can calculate corrections for the first.
Now, let's look at our first example on finding the interval of convergence of a power series. In this question, we are given a power series and need to determine all values of x for which the series converges. To solve this question, we first apply the ratio test. We need to calculate the limit of the absolute value of the ratio between two consecutive terms as n approaches infinity. After simplifying the expression, we compare the result with 1. This allows us to determine the radius of convergence, which we denote by r. Once the radius is found, we write the interval as modulus x minus a less than r, where a is the center of the power series. Finally, we test the endpoints separately because the ratio test does not tell us whether the series converges at those values. After checking the endpoints, we obtain the final interval of convergence, which tell us exactly where the power series is valid. Next, let's see how a function can be represented as a power series. In this example, our goal is to express the given function as an infinite series centered at a specific point, usually x equals to 0, which is known as a Maclaurin series. We begin by using a known power series formula or manipulating an existing series to match the given function. After obtaining the general form of the power series, we determine its radius of convergence using the ratio test. Then, we check the endpoints individually to determine whether they should be included in the interval. Therefore, our final answer consists of two parts. First, the power series representation of the function and its interval of convergence. This example shows how power series can be used to rewrite functions into an infinite polynomial form, making them easier to analyze and approximate. To conclude, power series are important mathematical tools that help us represent and approximate function. By determining the radius and interval of convergence, we can identify where a power series is valid. As we have seen from the examples and applications, power series are widely used in mathematics, science, and engineering to solve complex problems more efficiently.